sklearn, linear model, perceptron. Description. The perceptron is a linear model for binary classification. It learns a hyperplane that separates the data into two classes. It is a simple and efficient algorithm. But it is sensitive to the scaling of the features and can be prone to overfitting. Inputs. X the training input samples. It should be a 2D array of shape n samples. N features, where n samples is the number of samples and n features is the number of features. Y the target values. It should be a 1D array of shape n samples, where n samples is the number of samples. The values in Y should be either 1 or -1, representing the two classes. Outputs. Coa the weights assigned to the features. It is a 2D array of shape n features. 1, where n features is the number of features. Intercept the bias term. It is a 1D array of shape 1, which is a scalar value. Kniter the number of iterations the algorithm ran. Steps. The algorithm starts with a random set of weights. For each training sample, it calculates the weighted sum of the features. If the weighted sum is greater than or equal to the threshold 0 in this case, it predicts a class of 1. Otherwise, it predicts a class of -1. If the prediction is incorrect, it updates the weights by adding the features of the misclassified sample to the weights if the prediction was -1, or subtracting them if the prediction was 1. The algorithm repeats these steps until the weights converge or a maximum number of iterations is reached. Metrics. Accuracy: the percentage of correctly classified samples. It is calculated as the number of correctly classified samples divided by the total number of samples. Precision: the percentage of correctly classified positive samples. It is calculated as the number of true positive samples divided by the sum of true positive and false positive samples. Recall: the percentage of positive samples that are correctly classified. It is calculated as the number of true positive samples divided by the sum of true positive and false negative samples. F1 score: the harmonic mean of precision and recall. It is calculated as 2 precision recall. Visualization plots. Decision boundary: a plot that shows the hyperplane learned by the algorithm. The hyperplane separates the data into two classes. Confusion matrix: a table that shows the number of true positive, true negative, false positive, and false negative samples. Fine-tune parameters. Penalty: the penalty term to be added to the loss function. It can be L1, L2, or elastic net. The default is L2. Alpha: the regularization parameter. It controls the strength of the penalty term. The default is 0.0001. Fit: intercept: whether to fit an intercept term. The default is true. Maxiter: the maximum number of iterations to run the algorithm. The default is 1000. Toll: the tolerance for the stopping criterion. The default is 1e-3. Shuffle: whether to shuffle the training data before each iteration. The default is true. Random state: the random seed used to shuffle the training data. The default is none. Uncertainty methods. Confidence score: the confidence score is the probability of the predicted class. It is calculated as the output of the sigmoid function, which is a function that maps a real number to a probability between 0 and 1. Challenges and fixes. Challenge 1: overfitting. The perceptron can overfit the training data, especially when the data is noisy or the number of features is large. Sample use case that resulted in challenge 1: training a perceptron on a dataset with a small number of samples and a large number of features. Fixes to challenge 1: regularization, cross-validation, and early stopping. Challenge 2: sensitivity to scaling. The perceptron is sensitive to the scaling of the features. If the features have different scales, the algorithm may favor features with larger scales. Sample use case that resulted in challenge 2 training a perceptron on a dataset with features that have different scales. For example, one feature is in meters and another feature is in kilometers. Fixes to challenge 2 feature scaling techniques, such as standardization or normalization. Challenge 3 nonlinear data. The perceptron is a linear model, so it cannot learn nonlinear decision boundaries. Sample use case that resulted in challenge 3 training a perceptron on a dataset with a nonlinear decision boundary. For example, a XOR dataset. Fixes to challenge 3 use a nonlinear model, such as a support vector machine SVM with a kernel or a neural network.